Hello, everyone. Welcome to the 2024 IEEE Western New York Image and Signal Processing Workshop. Today we'll be discussing an innovative approach in computer vision titled Robust Bayesian Vision Transformer for Image Classification. Here is the presentation outline. We'll start with motivation, our problem statement, and our proposed approach, with our methodology, experimental analysis, and future direction with our conclusion. Let's start with the motivation behind this research. Image classification plays a critical role in several high-stakes applications like airport security, autonomous driving, and medical imaging. In these scenarios, even minor errors can have serious consequences. As models are applied to these areas, it's crucial to improve their robustness, especially in unpredictable or noisy conditions. The VisionTransformer, a state-of-the-art model originally designed for natural language processing, has shown great promise in capturing long-range dependencies in images. However, while vision transformers excel in understanding complex image features, they lack robustness in noisy conditions and fail to provide measures of uncertainty. This limitation is particularly problematic in applications like healthcare and autonomous systems, where a reliable confidence measure is essential. The problem we're addressing is twofold. First, deterministic vision transformer models are not robust enough against noisy conditions and adversarial attacks, which could distort their performance. Second, these models cannot measure their uncertainty or confidence in their predictions. For high-stakes applications, this lack of self-awareness in the model can lead to severe consequences, as the model cannot signal when its predictions might be unreliable. To tackle these issues, we developed a robust and trustworthy framework using a Bayesian vision transformer called BayesVIT. By incorporating Bayesian inference, our models can provide both predictions and measures of uncertainty. The key idea is to propagate the first two moments of the variational posterior distribution over the model's parameters through each layer. This allows the models to simultaneously compute the mean, representing the output prediction, and a covariance matrix, representing uncertainty. This uncertainty can serve as a warning signal for the user if the model's output may be influenced by perturbations or noise. In practice, we simplify the computation by focusing on the diagonal elements of the covariance matrix, which hold the most information about variance. Our work initially adopts the deterministic vision transformer that includes the extraction of input images into patches, apply linear embedding, and passing them into a self-attention mechanism, followed by a multi-layer perceptron layer to get the output prediction. However, our methodology is grounded in Bayesian learning theory. The difference is that we now consider the VAT in the Bayesian framework, where the weights of each layer are modeled as a distribution instead of having a single deterministic value, as it is in the general case that allows us to compute a distribution for prediction, as well as through which we can estimate the uncertainty. In Bayesian theory, we introduced prior distribution over the network weights. However, after we apply Bayes' rule, calculate the true posterior distribution that captures the total knowledge about the weights after observing the dataset, which computes the likelihood of probability across all weights, is mathematically intractable. Because Bayesian inference can be computational intractable due to the nonlinearities of a deep neural network layers and high dimensionality of the parameter space, we use approximation techniques called variation inference to model the true posterior distribution of the weights. The optimal parameters of the variation posterior, phi naught, are derived by minimizing the Kullback-Leibler, or the KL divergence, between the approximate and the true posterior. To make this feasible, we optimize an evidence lower bound function that balances model fit and regularization. This is the loss function based on the evidence lower bound function that we employ for our Bayesian VIT model. Specifically in the self-attention function, there are inner products between two random vectors, Hadamard products between random vectors, and nonlinear functions applied to the random vectors, in which Q of I and V of J are the weight matrices. The Curie key and value vectors represent the linear projection of the input sequence. D of K denotes the dimension of the key vector, Phi is the softmax function, and Omicron is the Hadamard product. Again, our main goal is to propagate the first two moments of the variational posterior distribution over the model's parameters through each layer, including attention layers, layer normalization, and nonlinear activation functions. This comprehensive uncertainty propagation allows our model to quantify its confidence in its predictions, giving a more nuanced understanding of classification outcomes. We're now going to closely examine in detail how the mean and variance are propagated through the attention layer, layer normalization, and nonlinear layers by deriving appropriate equations. So specifically to formulate the moment propagation through self-intention layers, we're going to have W of H and the Hth row of the vector of the weight matrix, where the matrix W, where H goes from 1 to 2 to H, and H is the number of hidden nodes. The variation distribution is in the following equation. The inner product between each pair of independent random vectors, W of H and X of I, can be written as the other following equation. So the mean and covariance of Q of I can be derived as follows below, where T indicates the matrix transpose operation and TR indicates trace of a matrix. And we can apply the same derivation to the Curie, key, and value tensors. So for layer normalization, consider d-dimensional input vectors of a layer over a mini batch of size m. Then the output of a layer normalization transform per ith data sample is given by the equation below, where mu of b and sigma squared b are the sample mean and variance over the mini batch, and the other two are hyperparameters for scaling and shifting the input, and E is constant to ensure numerical stability. Since the variables are deterministic quantities, then the propagation of the first two moments through the ln is derived as the equation below, where diag x is a diagonal matrix whose diagonal entries are the entries of the column vector x, and omicron is the Hodman product. For nonlinear functions, the first order Taylor series approximates the mean and covariance matrix after the nonlinear activation functions in the model, including the softmax function. Thus, the mean and covariance are derived in the equations below, where J of phi denotes the Jacobian matrix of A hat of I with respect to AI evaluated at mu of A, and the mean and covariance matrix of the element-wise multiplication and Z of I are derived as follows, the equations below, where D and mu V of J represents the diagonal matrix whose entries are given by the column vector mu V of J. Our experiments compare Bayes VAT with both the deterministic Vision transformer and Bayes former, a transformer model that utilizes a Monte Carlo dropout to enhance the robustness and exhibit the Bayesian nature for uncertainty estimation. We tested these models on the MNIST dataset, running trials in both noise-free and noisy environments, where we added Gaussian noise and used adversarial attacks like the fast gradient sine method and projected gradient descent. We ensured a fair comparison by using consistent hyperparameters across all models and datasets. We are currently extending experiments to Fashion MNIST and CFAR 10. This setup allows us to compare how well each model handles adverse conditions and how effectively it can communicate uncertainty. And for our experiments, we use the MNIST dataset, a benchmark dataset for handwritten digit recognition. MNIST includes 60,000 training images and 10,000 test images, all at a resolution of 28 by 28 pixels in grayscale. This dataset provides a controlled environment to assess the model's performance under noisy conditions and adversarial perturbations. Our results in the MNIST dataset indicate that Bayes VAT demonstrates improved robustness under high noise levels and stronger adversarial attacks compared to deterministic NMC dropout models. You can see the green column, the VDP, was our model, and the accuracy is overall better than the Bayes former model. The following graphs also display that our model has a higher accuracy and larger noise levels than the Bayes former model. Notably, the Bayes VAT adjusts its uncertainty levels in response to noise. From this graph, we can observe the predicted variance of the model increases as the signal-to-noise ratio decreases. This specific behavior allows the model to act as its own performance monitor, alerting users when predictions might be unreliable due to noise or adversarial attacks. So overall, the Bayes VIT model exhibits robustness and self-awareness, making it a valuable tool for applications where reliability is critical. This model's ability to adjust its uncertainty based on the noise levels and perturbations can enhance decision-making in high-stakes fields by notifying users when predictions may be unreliable. And for future work, we aim to expand our experiments to additional datasets such as Fashion MNIST and CIFAR-10, and scale the model to larger datasets like ImageNet. We also envision real-world applications including medical imaging, where robust and uncertainty-aware models could make a significant impact. Here are some of the references, and thank you for your time.